So welcome back, everyone. Welcome back to the mentor stream. So we've got a series of lightning talks at the code sprint. And the next talk over the next 30 minutes will be by Devon Sokul. Without further delay, over to you, Devon.
All right, thank you. I'll go ahead and share my screen.
Okay, yeah, we see it.
Okay, great. Okay, yeah, good morning, everyone. Well, for me, it's 4 a.m. here. I'm on Mountain Time Zone, so it's pretty early in the morning for me. But I'm Devon Suku, and I'm a contractor for NGA. So I'm a software developer, so I support them, writing software as the IDO and gaming gets developed. And my topic for today is how the IDO uses GeoSPARQL. Okay, so this is my plan for the presentation. So up front, I'll just answer the question how the IDO uses GeoSPARQL. That'll be attempt number 1. Now, while the answer is actually, it's not too complicated, there's a lot of prerequisite knowledge for this to make sense or have any meaning. So the rest of the presentation, I'll be providing context and maybe preliminary information that would be helpful in knowing that. And then I'll revisit the answer again, and hopefully the second time it'll make more sense. I think it'll be a little bit confusing up front if you're not familiar with all these things that's listed there. Okay, so the question, so how does the IDO use GeoSPARQL? And this is what I would say. So while the IDO stores geodetic information using CCO, it also permits the redundant encoding of GeoSPARQL's well-known text string literals, which enables GeoSPARQL functions within SPARQL queries. It's kind of a mouthful. Again, if you're not familiar with all that terminology, this probably won't make sense, but ideally by the end of this presentation, this will make sense to you. So I'll start with the basics, is what is RDF? And I realize that this is very new for a lot of people, so I'm really trying to break this down just so it's a little bit more familiar with everyone. But RDF stands for the Resource Description Framework. It's a W3 standard for representing data as triples. So a triple is a statement of information structured as subject, predicate, object. And these triples come together to form a graph-like structure that we call a knowledge graph. So here's some example of just some dummy data, and it's organized in the form of a triple. So animal is a creature, dog is an animal, Waffles is a dog, and Waffles has weight 300 pounds. Again, everything is subject, predicate, and object. So why are triples so important? Well, going back to RDF, like why is it like this? So a triple forces the data to be described in a complete coherent sentence. So for example, maybe in a traditional file, we just put in a coordinate and we say the latitude is first, or maybe it was the longitude. I can't remember which one it was. Sometimes we might mix them up. But in RDF, we have to say the coordinate has latitude, provide the value. The coordinate has longitude, provide the value. The order doesn't matter. You could swap the values. You can even separate the two statements, but each statement is an independent statement of information. And so the data is self-describing. Now, doing this is very verbose. It takes up a lot of space, but there's a lot of advantages to having this self-describing data model. What is an IRI? I'll run through this briefly, but so our RDF uses IRIs for everything. IRI stands for internationalized resource identifier. RDF uses IRIs to uniquely identify content. So let's say we have our dummy data. Each subject, predicate, and an object basically gets an IRI. So the classes get IRIs, the properties get IRIs, the instances of data get IRIs, everything gets IRIs. And each IRI identifies a particular piece of content. Okay, so how does GIME link up with RDF? So GIME provides a content ID that uniquely identifies a piece of content. That content ID will be used in the GIME file as an IRI as the subject of a list of triples. So on the left, we have a GIME file, defines a content ID. On the right, that same content ID is listed as the subject of a list of triples. And here are the list of triples describing the image. The RDF file is very flexible. You're free to describe the image however you wish. So again, RDF is independent location, this means that no information is inferred by the location of the triples. This is a very big difference from RDF to other formats. In most formats, you assume things about a value depending on its location. Not so with RDF. So in the previous example, we had an RDF file with a list of triples. If you took that same file and broke it up into different RDF files, this is exactly equivalent. This conveys the same exact information. So you could separate the triples into different files, rename the files, move them around. It doesn't matter. They convey the exact same information because RDF is location independent. So this is the reason why you can put the RDF inside the GIME file or outside the GIME file. Again, because an RDF file is just a list of triples, and each triple is an independent, complete statement of information. Now, while you do have the option to store the RDF inside and outside the file, storing the RDF outside the file is by far the more important use case. And I'm hoping to demonstrate why that is a little bit later in the talk. Okay, so RDF contradictions. So what happens if two RDF files contradict each other? Well, this is the purpose of SHACL. I'll just say that SHACL is the shapes constraint language, and it's a tool used to validate RDF data. So if there's any inconsistencies or errors, so SHACL is responsible for catching them. SPARQL. Okay, so SPARQL, we can't talk about GeoSPARQL without SPARQL. So SPARQL stands for SPARQL Protocol and RDF Query Language. SPARQL is the query language for RDF. It's very similar to SQL, if you've ever done any work with SQL. And here's a very simple example of a SPARQL query. So again, in a typical workflow, we'll have all the RDF files will go into a triple store, which is some kind of data structure. It's usually a database, or they can also be in memory. But regardless, all RDF files will be collected together, which allows the user to query against them. And I guess this goes back to, this is why having the RDF file outside the GIME file is very important, because then it's able to be loaded into a triple store and queried with SPARQL. If it's locked inside the file, then it has to be parsed out anyway, and then put in the triple store in order to be queried. So maybe I'll go back to, so again, maybe for small niche scenarios, you only have a few files. There are situations like that where having the RDF in the file might be useful. But again, we really want them, in practice, we'll be having them outside most of the time. to place into triple stores to be queried. Okay, a demo is worth 1,000 slides. So let's look at a demo real quick. I wish I was there in person. I would ask, any fans of Wikipedia? I love Wikipedia. And there's actually a publicly available website you can go to called Wikidata, which allows you to query data using RDF. So you can query the entire Wikidata database with SPARQL. And so this is a SPARQL interface. You can write your own SPARQL query here. But they have some examples for you just to get you started. So for example, the cats query. If I wanted to query for all images of cats, I can just write the appropriate SPARQL query and run that. And let's see. This usually happens really quick. I'm not sure what's going on with my bandwidth. Okay, this depends on my internet. Let's try a different query. How about pictures of horses? Well, that's too bad. I'm not sure what's going on here, but yeah, I think there's.
How about refreshing the page? Maybe that's.
Yeah. Yeah, I'll refresh the page. Oh, there we go. That works very well. Okay. Great. Yeah, it's Gobi. I want the cats demo. I want to see pictures of cats. Yeah, maybe it's that one. Okay, I'll forget the cat's picture. But anyway, these are just some examples. What's cool about SPARQL is you can query on everything. There's literally nothing in RDF that you can't query on. If it's in the database, you can write a query on it. And so there's just hundreds of examples of things you can query on. Senses of sweetest phrases in lexemes. It's the most famous child of a librarian. I don't know. I'll do one more. So rivers in Antarctica. That sounds more geospatial related. So maybe I'll try that. Anyway, I'll stop there for now. Anyway, I encourage you to try the Wikidata RDF querying, and hopefully by doing so, you kind of realize how powerful it is. I was hoping that demo would go a little bit better, but I'm just going to move on for now. Okay, so again, yeah, let's see, just I'm halfway point. This is just a reminder for me to see where I'm at. Let's see. And I'm about halfway with time, so that's good. Okay, so real quick, so when I say ontology, that's really just a type of data model. Never say that to an ontologist, but for the purposes of today, we'll just say that ontology is a data model. So there's three kind of levels of ontologies: top layer, middle level, and domain level. The IDO, of course, stands for Imagery Domain Ontologies, sits at the domain level. But I'll briefly talk about the top level ontology, BFO. BFO stands for Basic Formal Ontology. And I won't go into any details about this, but I'll just say that we have a requirement to be BFO compliant. So whatever our ontologies we use has to conform to BFO. And then BFO sits at the top layer, so everything else is a subclass off of BFO. CCO, the Common Core Ontologies, this is a middle level ontology. So it's CCO derives from BFO, and we don't have a strict requirement to use CCO, but let's see. It's nice to use because it is BFO aligned, which we're required to comply with, and it has a geospatial ontology, which is useful for this for kind of what we're doing. And finally, the IDO imagery domain ontologies. The domain ontology is the lowest level of abstraction. The IDO is responsible for supporting all types of imagery metadata. So not just geospatial. Geospatial is just one subset of metadata we're trying to support. And the IDO is still in the draft phase. So everything is subject to change, and now is a great time for feedback. I'll skip through this, but just another high-level overview. At the top level, we have BFO, which everything is derived of. CCO, the middle level, is an intermediate ontology that the IDO derives from. And again, just want to convey that the IDO doesn't just cover geospatial data; it covers all types of data collected from sensors and cameras. So the scope is really quite large. Okay, so with the IDO, how do we currently store coordinates? Well, first thing, we do not use bounding boxes. This is instead of bounding boxes, we use something called a correspondence group, and the correspondence group links a list of pixel coordinates to corresponding set of ground coordinates. And a list of these is what's called a correspondence group. And they don't have to be the four corners of the image. They can form arbitrary polygons. But the correspondence group is how coordinates are stored in the IDO using RDF. Okay, so GeoSPARQL. GeoSPARQL is an OGC ontology that adopted well-known text to encode coordinates as string literals. Here are some examples of well-known text literals. So you can define points, lines, polygons. If I could summarize GeoSPARQL into two classes, it would be these two. It defines a feature, which represents things in the real world, and a geometry, which is the spatial representation of the feature. So here's an RDF example of a GeoSPARQL point. At the top, the first set of triples, we have the IRI for a feature. And the second set of triples is the IRI for a geometry that defines the geometry for that feature. So from a class perspective, GeoSPARQL is very simple. It's really just these two classes, feature and geometry. In addition to classes, GeoSPARQL defines a list of functions. They define a list of geospatial functions that can be executed in SPARQL. And this is really the power behind GeoSPARQL, is these functions. My personal favorite are these two, GeoSF within. It checks if one geometry is inside another. So this is useful. You could draw a bounding box and you can query for all data that falls within that bounding box. And then the distance function, you can check the distance between two geometries. So going back to well-known text, let's say we have a point and a polygon, and you want the distance between the two. That might be somewhat difficult to compute by yourself, but it will find the closest point on the polygon. It's the point and calculate the distance between the two. So these are just two of many functions listed within the GeoSPARQL specification. One more demo. I don't know if I want to do another demo, but there's another online demo called QLever. And it has more, kind of like before, it has more SPARQL queries. But there's more geospatial, but this one queries on OpenStreetMaps. And it uses GeoSPARQL to query on geospatial data. So if I want, let's see, all streets in a particular highway, I can run that query. Oh, great, that worked. I can get all the streets in a particular area and display that on a map view. for example. So I think this gets all the streets within a city, and I can browse that from the SPARQL query. Let's see, and there's all kinds of things you can query on. Maybe I want all castles in the world. Well, I can write a SPARQL query to query for all castles. Run the query. Okay, great. That was relatively fast. And then view that in the map. So these are, looks like all castles inside of Europe. So again, it's called QLever. This is a free and open source demo. You can go online right now. And there's just tons of things you can query on. Like literally, like if it's an RDF, there's literally nothing you can't query on. Oh, this one looks interesting. The power network of the IDO. I feel like that's something you shouldn't be able to query on, but I'm kind of curious about this one. Oh, never mind. Okay. Anyway, so this is an example of an application that uses GeoSPARQL, and it's tremendously useful just being able to query on the information to get what you want. Okay, let's see. Currently, okay, so currently, again, the IDO uses CCO to encode coordinates. Optionally, the users may use GeoSPARQL well-known text to encode their coordinates. And when they use the well-known text, that enables the GeoSPARQL functionality that I was demoing before. So why encode the coordinates twice? So there's a bit of a competition between the two standards, CCO and GeoSPARQL. They both define mechanisms for encoding coordinates. This is really inconvenient for us because we have to kind of decide which one to use. And currently the IDO is designed to use CCO. So CCO is one, it's BFO aligned, and it stores the values in native triples, which is relatively nice. It's also very easy to extend, but there's no spatial indexing. So if you want to do spatial queries or functions, you're kind of on your own for that. So that's why we use GeoSPARQL for geospatial applications. It provides all these geospatial functions and the spatial indexing. It's unfortunately not BFO aligned, and it doesn't support all of NGA use cases. It just supports GeoSPARQL use. Excuse me. It only supports geospatial applications, and the coordinates are encoded in a string literal, which is mildly inconvenient. Okay, but so feedback from testbed 21. So Simon was working on this all throughout the testbed 21. He proposed that we just use well-known text for everything. And GeoSPARQL, it's not BFO aligned, but it can be extended to be BFO aligned. It doesn't support all of NGA use cases, but it can be extended to do so. And so this is something we're kind of looking into. Can GeoSPARQL be extended to fit the bill for everything we need? And if it can, it would be really nice to just use one encoding mechanism. And then we wouldn't have to split this up between the two encoding mechanisms. I'll skip this for now. Okay, so I'll wrap up the talk. I'll answer the question one more time. So how does the IDO use GeoSPARQL? Well, the IDO stores the geodetic information in CCO primarily. But users can also redundantly store the GeoSPARQL well-known text as string literals. That enables geospatial functions within SPARQL queries. Okay, that's it for my talk. Hopefully that was helpful in understanding RDF and GeoSPARQL a little bit better. But that's it for my talk. Thank you.
Thanks, Devin. Okay, are there any questions or comments for Devin?
One question.
Sure, go on, Sina.
Devin, can you go back to the slide that you were showing the ground control points, the ground coordinates and the coordinate points? Yeah, this one. So this transformation, do you also record like store what's the equations gonna be like? Is it a bicubic? Is it like a polynomial, or how does it how does it does this calculation? Like, does it care, or you have to store it for every pixel, because that would be really hard. So that I don't understand.
No, the correspondence group, it's just for storing these 4 points. And it's just saying that that this point corresponds to this ground coordinate. And then that point corresponds to that ground coordinate. That's all it's saying. Other information like saying the transformation, other things you want to describe, you would use a different set of triples to describe that information.
Makes sense.
Okay, thanks. There's another question.
Martin? It's just I can develop a little bit on this topic. It's our story about affine transform, those kind of things, could be rephrased in another way. If we want to avoid any ambiguity, we need to provide the function which goes from pixel coordinate to ground coordinate, no matter how we express the function. The problem with bounding box and stuff like that is that we do not express the function. We express something else, and then we have to guess the function from that. And there is ambiguity in the process of guessing the function from the bounding box. If the function is provided explicitly like that, or no matter how it is expressed, it is non-ambiguous. So this way is non-ambiguous. Let's say the F5 provide a grid of point, which is exactly what you said. They provide the coordinate for every pixel, which is non-ambiguous. The affine transform is just a way to encode the formula in the special case where the formula is linear. So it's one special case, but the important thing is that we encode the function. We don't provide something else and ask user to guess the function from that.
Okay.
So anyway, where we encode explicitly the function is fine.
Yeah. Okay.
Just a follow-up comment on that. So yeah, just again, we are not using bounding boxes. I heard the term bounding box, and I just want to reiterate, we are not using bounding boxes.
Makes sense.
Yeah, we're using correspondence groups. And in addition to this, we can provide the affine transform or any other transformation functions that may be necessary. The RDF is very extendable, so we can extend it to and add whatever we need.
Yeah. Okay, thanks. And I've got a comment. So one of the cool things about GeoSPARQL is that you can actually assign coordinate reference systems to, you can state the coordinate reference system that a coordinate is referenced to, or reference, let me say, assigned to. You can state that in the actual string. And there's an example. There we go, right there. So on there, for instance, yeah. So on there, that immediately tells us that the WKT point with coordinates represented there. It's reference to the Earth using the CRS-84, which is WGS-84. Longitude, latitude aligned coordinate reference system. So that is quite a powerful capability, because it means that we can use any coordinate reference system, and that means that it opens up a whole suite of scenario of use cases, etc. But what I wanted to point out is that we recently, I think maybe in the past 6 or slightly more months, we started an effort. This is an effort started by the Geosemantics domain working group, to create an ontology, an RDF representation of the ISO 19111 standard, which defines the coordinate reference system model, or the logical model for coordinate reference systems. So what that potentially means is that, there could be an opportunity in the near future to not just reference a coordinate reference system, but also to describe its its definition using RDF. We currently do that using WKT and GML. So the GML, but the GML one is slightly outdated. It uses a previous version of ISO 11111. But WKT2 that supports the latest version of ISO 19111. So if that ontology, once that ontology is completed, or the RDF representation of 19111, once it's completed, we might be able to represent everything on there using RDF. But I've just made a mental note to make sure that the team that's working on that, they should look at BFO alignment as well. So that's that's something we'll need to make sure that the geosemantics domain working group is aware of in terms of BFO alignment, and at least to try and support it or align with it as much as they can. So right.
Yeah, just one more comment off you, Gobi, just since you were talking about this. So in GeoSPARQL, you can specify the coordinate reference system. But one of the decisions for you going with CCO over well-known text as the primary way of encoding was we weren't sure if well-known text was able to encode all of our coordinate reference systems. So it supports you can specify a coordinate reference system, but it's unclear to us whether it supports coordinates on other planets or moons relative to a platform, ECI coordinates, upward-looking images, azimuth elevation range. These are coordinate reference systems we want to support, and the question is, does GeoSPARQL support this already, or if not, can it be extended to support them? And so there's a few. I know you've responded to this, and there's a few documents that we need to go through. But any information or insight or demos relating to the support for maybe other types of coordinate reference systems, that would be really useful for us to know, and work that's going on extending GeoSPARQL. That's very important for us to know. So
okay.
that might be a good task to work on during the code sprint or afterward. So.
Yeah. Well, that's awesome. Thanks, Devin, for sharing this slide. I do recall some of the discussions, but it's good that you presented it in a single slide, because it's now I remember some of the discussions, and I think that would certainly be worth doing, and I'll make sure. I'll make sure Joan Maso and Nuria are also that they also keep this in mind, because there have been some activities done around planetary coordinate reference systems, etc. But I think pulling that together into into a section in one of the upcoming reports, probably the D206 report, I think that would be helpful. But cool. Sorry, Sina has got a comment.
Yeah, I have another question, Devin. So you've mentioned one coordinate, basically transformation. Can this be extended to have, like, if you have if you do want to, for example, have engineering CRS, like imagine that you store multiple images and that would be GeoStreamer or libheaf, like will be a stream of images, let's put it this way. And each one would have its own basically CRS, which is very often in the like a out in the space kind of challenges. Do you also be able to like store their coordinate like this correspondences that you showed in a separate basically part of the turtle file, or it's gonna be just one value per? Yeah.
Yeah. Okay, so let's see. Yeah, it corresponds. All it does is it links a pixel coordinate to, I guess I'm saying ground coordinate here, but it links into a coordinate, and that coordinate can have any coordinate reference system. In fact, it can point to all four of these could have different coordinate reference systems. That's technically not restricted, though that would be painful to work with. So yeah, so different images can have different coordinate reference systems. The correspondence group is agnostic to which CRS is being used.
Yes, so
So
but it will be a two-step process actually. So usually the process that I suggest is that the engineering CRS stay the same, does not change. What changed for every image is this function.
Yes.
So we have one engineering CRS that stay always the same. This function may be specific to each image, to change to each image.
If you work with oblique imagery, if that's the nadir imagery, right? If you work with oblique imagery, the CRS might change even from a frame to frame, because your tilt and yaw and stuff like that will change the whole CRS.
It depends how we define the CRS. So if we define the CRS as what the camera see, no matter the orientation of the, if we define the CRS as the engineering CRS that as something which is fixed relative to the camera, even if the spacecraft move, the camera move,
the starting point is going to be the same. I see your point.
Yes, the engineering CRS stayed the same. So the engineering CRS just said the point on my left, the point on my right, the point in front of me, not knowing the orientation of the spacecraft.
Right, and that's a part that I was actually very confused. So in that case, you have to store the pose of the camera in a separate format.
That's part that could be part of the trajectory. So we have an engineering CRS which is fixed. We have a function that gives for each pixel, which give the coordinate relative to the engineering CRS. So it's depends on how we define the engineering CRS. Then we can have a moving feature or other data structure that give at every time the position of the spacecraft and the orientation, all those things.
Right.
And then we have yet another step going from the engineering CRS to the world.
So Devin, are you planning to are you planning to also support something like moving features in this?
yes, moving, yes, absolutely, yeah.
Okay.
Yeah, so the target's moving through a frame of video.
Yeah, because Lucio is actually working on this. So he has a drone right now in this code sprint. He has a drone set of imagery, and he has a moving feature kind of a file for it because it has the coordinates of the drone. I was thinking, he had this question that should we store the moving feature as a moving feature, which is like a temporal variation of the trajectory, or should you store frame by frame, like consider like every 5 seconds, every 10 seconds? And frankly, I don't have an answer for that. I don't know how Gimme is planning to support that. And the reason for it that I'm asking this is that if you consider the whole trajectory, then you have to do post-processing, right? Because then you have to have the CRS, you have to come calculate the pose, and you figure out the coordinates later on. If you do frame by frame, it's like it's really not a moving feature. It's like you have a frame, you have coordinates basically calculated, another frame coordinates calculated. So I assume that when you say moving features, you are really thinking about the trajectory. Is that the right assumption?
I'll just say that I don't know. I'm probably not the person to ask about that.
Okay.
Okay. But I'm not sure either. But I'll just say that we really want to store all metadata in RDF. So that's kind of we're going with the RDF format. Kind of how we do that exactly is up for discussion and
makes sense.
And again, the power behind the RDF is the queryability. It's no matter how it's in the RDF, we can query across all images with track data and all images at an area at a time. It's really the queryability that is the power that we're looking for. But again, yeah, great. That's something we should look into discussing further.
For sure. I see Rob's hands raised.
Yeah, Rob.
Hello. Yes, you were talking about video, so you piqued my interest. Yeah, I think you're right, Sina, that a very good definition of a moving feature is something with a trajectory. It doesn't have to move, it can have zero speed. The other complication in this, you've talked about a static camera looking at moving objects. The camera itself may be on the move as well. That's certainly true for satellites. But even at ground level, if you have a moving camera observing static objects, it's the same problem as a static camera observing moving objects. So that there's definitely a symmetry there. The other thing to say is whatever you do, there has to be a simple version of it, because often these devices are very simple and autonomous, and they don't have access to coordinate reference systems and so forth. So it's just store the data, and post-processing is the way to go. Do the simplest possible thing. And the simplest possible thing is spotting sight lines. There's a feature I know, there's a pixel I know, okay, and I know where I am, and we can work it out from there. So that's certainly something to think about. But yeah, it's Pandora's box when you open that one, I'm afraid.
Okay,
Hope that helps.
Yeah, no, it does. It does. And I've just I think we've run out of time, but it's been a great presentation. Thank you, Devin, for for sharing that with us. So the code sprint continues. But a number of well, I mean, the participants are working on the various activities, but we also have a number of lightning talks later on. I think you've got the FMSDI one later on, Sina?
And the DGGS.
DGGS, right?
Yes.
AI for discrete global grid systems.
Yes.
Yeah. So there's still quite a lot to explore at the code sprint. So thanks again, everyone, and we look forward to seeing you in the other sessions later.